Okay. Buenos días a todos. La Dirección de Investigación Pesquera en el Pacífico estará organizando una serie de seminarios de investigación con la finalidad de que investigadores del INVIPAS y de otros centros de investigación pues puedan presentar las investigaciones que realizan y en ese sentido se puedan generar sinergias de colaboración entre las diferentes instituciones. En ese sentido, hoy tenemos la presencia del doctor Yasek, que es nuestro primer invitado a esta serie de conferencias y me voy a permitir leer una pequeña semblanza del doctor. El doctor Yasek Krause es profesor asociado honorario de la Escuela de Matemáticas y Estadística de la Universidad de Sydney, en Australia. Ha trabajado con enfoques de control óptimo y ciencias de la computación a lo largo de su carrera en diversas instituciones, entre ellas el Instituto de Investigación de Sistemas de la Academia de Ciencias de Polonia, la Escuela de Economía y Finanzas de la Universidad de Victoria en Wellington, Nueva Zelanda, y la sección de graduados del ESIME del Instituto Politécnico Nacional. El doctor tiene más de 70 publicaciones arbitradas, cerca de 3.000 citas de acuerdo con Google Scholar, que documentan su investigación en modelación matemática de procesos medioambientales, ingeniería financiera, asesoramiento en política monetaria, optimización, bienestar intergeneracional, políticas públicas y soluciones informáticas a problemas complejos de gestión y economía. Actualmente, el doctor es miembro del consejo editorial de la revista Environmental Modeling and Assessment, es miembro del consejo editorial de la revista Decision Making and Manufacturing and Services y es editor asociado de la revista Matemática Aplicaciones. Así que, doctor, bienvenido. Adelante, por favor.
Thank you very much for my seminar, coming to the seminar. And I will speak in English, me defiendo en español, pero aparentemente mudeo más en español que en inglés. So, as I say, I think I start a little bit less in English than in Spanish, so my seminar will be in English. But you are free to stop me with your questions, and I can handle, I think, your questions in Spanish. I've got here Pizarro, and I can probably explain things if necessary during the presentation. So, as you can see, well, the main term in this seminar is viability theory. So, what's viability theory? That's a counterpart of optimization. Everybody knows what optimization means when we want to be at some top of a mountain or just in the bottom of a trench or things like that. And not always we can actually reach that optimum. And even on paper, we present something as optimal, and we are conveying this to a manager. And the manager says, this is not necessarily something which I will apply because the model is always a model, has not allowed for some very difficult to formulate mathematically constraints. So in a way, viability theory is a solution to that difficult optimization problem. Is proposing a practical framework for managing things which we would like to optimize, but not always have all the information which enables us to construct a mathematical model. Because what I am imagining, well, as I'm a researcher, but I have still some experience in practice that, okay, so here we have a physical or biological or economical process. And well, after that process has been studied, some people like myself are proposing a mathematical model. And with this mathematical model, I will propose an optimal strategy. But the manager who helped me to understand the process might have questions about the applicability or feasibility or viability of that solution which I can propose based on the model. So I hope that you will see that I'm trying to somehow avoid that problem and formulate it still mathematically and in a rigid fashion as a problem of viability theory.
Okay, that's right again.
Okay. So, Professor, that's a summary of what I have just said, that the viability theory, which I will be abbreviating as VT, offers a broader mathematical framework than traditional optimization or stability analysis, providing a powerful tool for modeling and solving diverse managerial economics problems. Okay. And managers often face a conflict between implementing rigid analytical solutions. Okay, so prepare a solution which is model perfect, but some of the constraints are hard to quantify, and the practical understanding of the modeler of those constraints is lacking. And unlike optimal solutions, which are typically unique, viability of viable solutions will be multiple. So they might be not the best, but available, feasible, viable. So, and if I propose that within that region, the manager can use the intuition or the knowledge which they were unable to transmit to me, so that I can build a mathematical model perfectly, because some constraints are on a process are felt by the manager, but not necessarily can be phrased like that. So the managers will be able to select a viable solution out of a set of solutions which I will be able to propose. And I hope to have enough time to introduce you to a case study in which I will illustrate how to use viability theory to fisheries management problem of bycatch. Okay, and viability theory is a child of many scientific branches. It starts from mathematics, but there is also bounded rationality in socioeconomics and sustainability in natural science. Right? It's a very fashionable problem to find a sustainable solution. But so I claim that viability theory helps that sustainability problem. In economics, especially this guy, Herbert Simon, was proposing satisficing solutions, and that's the name, which is a neologism, so you probably will not find it in a dictionary, but that's his original term. Satisficing, so is good enough, sort of, so safe enough to apply. And so if we think of a governor of the central bank, or the fishery manager, the director of a national park responsible for biodiversity. So in a national park, there should be some grizzly bears, right? But if there are too many of them, the tourists will stop coming. So you know it's not there is not an optimal number of grizzly bears. They may be between this and this. So that's what I mean that people like practical managers are seeking satisfying solutions that ensure compliance with specific standards. So this is my personal opinion that Simon's view is correct, that we should be looking for satisfying solutions, and I read that variability theory is offering mathematical tools to compute them. And now I would like to introduce a few examples. So imagine a waterfall, okay? So I might actually, well, draw something. So suppose that the waterfall is here at the length of x0, and it's so the waterfall is here, and the width of this is say 1. So, and you know that there is a current here, and if you settle the at this point, you will be sucked in and you will perish. But if you are a relatively good swimmer, depending on how the current is distributed, suppose that it's strongest here, a little bit less strong here and there. So if you are a good swimmer, probably if you keep yourself here, right, in that safe area, you will not be sucked into the waterfall. So this line is will be called the of points of no return. And this is a safe swimming area, right? Safe area, zone. And precisely when the variability theory tools will enable me to compute this boundary given what? Given the speed of the current and given the strength of my muscles as a swimmer. And there are some natural constraints, so like well, the distance and so this is what the variability theory should be able to compute. And similarly, so the stronger the river current becomes, the closer I am getting to the waterfall, and eventually at location 0, for sure, I will be sucked in. But I don't want to be here because I'm not strong enough to swim in this direction, and I will be sucked in. So you must maintain a safe distance, and this distance depends on your swimming skills. And here are some notation. So my skills, my controls are from a set. What sort of swimmer I am, and the mathematics of the current is also necessary to compute this boundary. So far, so good. Any questions? Okay, so now if you swim, and this will be the safe boundary area, right? The safe area boundary. And if you swim beyond this point, this limit, you will be sucked into the waterfall. So the collection of the safe distances is the boundary of the set of points of no return. And in fisheries, for instance, well, if you have a large biomass of something, fish or abalone or whatever, and you apply relatively high fishing mortality. So next year or next period, you will have smaller of that fish, obviously. And if you still keep on using this mortality level, then eventually you will end up with extinction. So, but certain biomass will still enable you to, well, you stop fishing or you fish much less or less, then you will be able to recover the fish biomass. So again, so I want you to see that the parallel, the correspondence between that relatively simple example of a waterfall and, for instance, the critical biomass of the fish, which corresponds to this boundary. If I am swimming here, if I manage my fishery in that safe area, and don't cross this boundary, which I have computed, given the numbers on biomass and on the fishing mortality, which I can adapt to, and that would be let's say the analog of what I was telling you here. So with the fish biomass, we also will have a point of no return, and that point of no return will be a boundary of the viability kernel. Okay, so this area is viable. I can swim here. If this is the well, this concerns the fishery. I know that with certain biomass in stock of the biomass, I will be able to safely operate for years from now to infinity or something, right? Okay, so determining the points of no return on the river, as well as the critical fish biomass and catch rate, is essential for safe journey. And by identifying the points of no return, we define the complement, the safe journey zone of viability curve. So if I have here the points of no return, the complement of the points of no return is the viability kernel, is the safe journey zone. And now the size of the viability kernel depends on what's available, what the strength of me as a swimmer I possess, right? In fishery is the viability, the strength is how many vessels I send to fish, and I'm in control of that. However, well, quite for optimization, most frequently you forget that you can't stop fishing from one day to the next, because people will revolt. People will have no money to live if you stop abruptly. But if you change it by 1% from period to period, then probably some people will retire, some people will emigrate, and you will end up with something which will be viable from the point of view of the fishery. So we are all in viability theory, we are looking for the viability kernel. So given a systems dynamics, so with the system dynamics is the equation of motion of water, of that current, equation of motion of biomass. So we need the systems dynamics, and then we need to know the constraints. So we know that we will not have more fish than the carrying capacity, and obviously zero is probably the very low limit, but for, I don't know, visual reasons, you want some lower bound on the on the fishery biomass. And the variability kernel, which I denote with that calligraphic V, is the variability kernel depends on the state of constraints. All constraints I have to allow for, and the system dynamics. So these are the points in the so-called state space, and from which I can start an evolution, and I will still remain in the constraint set. So I don't want to be sucked in, but this is too late. So if I stay here, I'm well safe. But I can swim here for the infinite time. So the variability kernel is the set of all points here, here, from which I can swim, and I will be I will survive. Sorry.
Doctor, could you please give us a small definition of the space states?
So sorry.
Working definition of state space.
State space. I will come. Yes. Okay. So state space. I will come. Hopefully, I will be able to. Okay. So this is it. Okay. Okay. Variability gates are usually determined numerically or graphically, because analytically it's a rather difficult problem. Okay. So here's an example of a state space. So this for Avalon, which we are discussing and working on with Carlos. If you divide Avalon into two classes, which are important from the reproduction point of view, dynamics point of view, or systems dynamics point of view, and economically, because if you have small Avalon, you are not selling it at all, or not selling much, and the large Avalon. So any point here in this positive constant, because you don't have negative fish, well, is a point in the state space. That's what we call. So if we have a dynamic system, we are trying to characterize it by the relevant numbers. So for the Avalon species, to be able to plot the problem, because we know that there are 30-something size groups of Avalon, but from the economic point of view, 2 are probably enough. And each of these points is a point in the so-called state space. So if I'm here and I know from history, from data I have gathered, that if nothing was fished at all, the next period would be here. So I'm not fishing. The small Avalon is growing, and the small Avalon is growing to become large Avalon, and I will be here, right? With low fishing mortality, I will be here. And with high fishing mortality, that probably I will the small Avalon, because I'm not fishing small Avalon a lot, or I'm not fishing much, so it will grow a little bit, but the large Avalon will definitely go down. So this is the systems dynamics in graphics. So what would be the equivalent of a swimmer? Well, where I am, the state space would be X, y. So every point is characterized by x and y. And if I have passed, I have missed this boundary, then I am in the no return area and things like that. So here also, probably if I put a boundary here that I don't want to, for various reasons, have less than this much of a large balloon. This may be equal 0 or something, and I can put some upper bounds because I know that the carrying capacity is such for some other reasons. So I will have an example of that set K, the set of constraints. The set of constraints will be from here to here, from here to here, something like that. So the set of constraints is also in the state space as the process we are considering. So A, B, C, D are the states of the abundant population. Okay, does this, thank you. Okay, and so mathematically, well, each of these states here, this is a very simple or the abstract example we might say. So what are these dx over dt? These are the velocities. So there's a velocity in the direction x, maybe, but x is the smaller balloon, and y is the larger balloon. And what this says? This says that the velocity here will grow the further I am from 0. If x is 0, this one is 1 times 0, then I have some situation, maybe a mountain. So if I am in the top of the mountain, so the distance from the top of the mountain is 0, then I will stay there. But if I move a little bit, then this becomes positive. So this becomes positive. So the velocity is positive. So I will go down the hill, right? Something like that. So this is an example of a mathematical model of a dynamic process. And I have controls here, right? And with these controls, I can probably stop if I have enough power to return. Right. And here is a little bit more advanced picture of that Avalon example. So I have constraint set K, this green area, and these arrows are well, showing the direction with certain velocities which are related. You can see that further from the center, I'm gaining velocity, right? Gaining velocity, and I am somehow moving to the west, something like that. So this is something which I have to figure out with biologists or economists. What is that systems dynamics? How these arrows are actually bent, and what is the strength of these guys? Because these guys will be able to change the direction of this arrow, but these guys can also be constrained, like my muscles, things like that, right? Okay. So here in this example, the further from the 0 point, the velocities increase and turn. And you should trust me, believe that with certain constraints on the velocities, for this systems dynamics, I can be safe in this ground area, and because I still have enough power to turn these arrows away. And now what does it mean? So it means that if I know the strength of my controllers, this is the safe area. It doesn't matter whether I put a little bit like that or like that, provided I'm using the actual values of the velocity which I have allowed for in constructing the model. And this is the safe area, right? This is the viability kernel, given the constraints K and the systems dynamics F. And if I'm here, I'm lost, right? Because I have no power to turn it so that the next step is within this green rectangle, right? Any questions? Okay. So what I am saying that the brown area is the safe journey area. The green area is the non-return zone, right? So now we can precisely have that policy description, because I was telling you that for a manager, I will tell him or her, here's the safe zone, and you can do whatever you want to do in this area. Use your imagination, intuition, things like that. So this is the notation. FR is the frontier or boundary. So if I am, and this means X, so wherever I am, that X can be vector, 2-dimensional, 5-dimensional, whatever. If I am in the viability kernel minus this is minus the boundary, then I can apply any control, right? Because if I'm here, I can do whatever I want to. But if I am at the boundary, I have to use the last resource stores to maintain the system in the constraints K. Because if I move here, I'm outside the viability kernel. I have no power to return to the safety zone. Okay. Why is this by the chance that? Okay, no. Okay, it's okay. So now sustainability problems. How do I go? Okay. I think you gave me an hour. Sort of, right? I think. But the important is that you catch the idea, and we can work out the examples later on. So sustainability problems arise when human interaction with a dynamic changing environment can potentially lead to catastrophic outcomes, right? So we know that there may be some hurricane or something, and which will destroy our fishery. So the interplay between the fish population and economic pressures can lead to resource extinction. Precisely, you have you want to catch as much as possible because you're greedy. But if you catch too much, next year you will be poorer. Okay, so I have to reduce the fishing mortality, but I can't do it from one day to the next, other than bit by bit. A sustainable solution requires maintaining the system within the safety zone, that brown circle, if you wish, or this area, or the biomass wealth within the bounds the set K has defined for us. And viability theory is a mathematical framework which helps you to establish this boundary and the viability term. So now a little bit of mathematics, but I'm not going in too much into excess. So notation. So this is the a vector of abalone sizes, and it can belong this velocity to what the system dynamics tells me, right? So F is that's a fancy system of belonging, of membership, rather than the equality, because equality would be if I exactly knew what the role, what the strategy, but I'm free within that brown area to select the strategy. So this formula describes all achievable ways the system can evolve. And there's a little bit of, you can't see, that's a philosophical interpretation of viability theory, right? I think in the regional investigation is probably more important than philosophical interpretation, but I want you to agree that this is philosophical interpretation. So this little equation or inclusion actually is the description of the fate. All right. So what the fate? Well, that's destiny. No. Yeah, destiny. Right. Okay. So this is destiny. So this is because I can't change how the fish reproduces. I can't change the current. So this is what the fate is. On the other hand, I have also my desire. So faith and desire is is the main point of viability theory, that I am able to satisfy my desire given faith. Because I would like to, I don't know, jump 3 meters. That's my desire, but the fate is that I can't, right? So something like that. So so collection of points which satisfy fate and desire is the viability kernel. Okay, so we can translate it into our private lives, what desires I have, but what money I also have, right? And so this is the fate and desire. Okay. Okay, so I have here a very simple example. I am starting with one species. So this is 15 years ago, Benet et al. I can give you references. So they, okay, there's one species which is perennial species of the given biomass X and vitamin D. E is fishing effort rate, so we will have how many vessels you sell. P is price, and catchability. C is the small c. This is what I catch, and this is for how much I sell it. And this is the fixed cost. So the profits will be described as this, right? So you've got price, you've got the biomass, you've got fishing effort. So fishing effort from 0 to 1 or from 0 to 100%, something like that. Catchability price minus fixed cost and variable cost, because the more vessels you set, the more you pay for that, right? And what are the equations? The equations are very simple. You can certainly know that this is the logistic equation. Okay, so we have carrying capacity, biomass. So if I'm below, this is positive and the fish grows. This is negative, fish goes down. And minus, what I'm taking off. So this is the speed of how my biomass changes. And I have to take care of the very important social sustainability constraint. And here is the differential inclusion. Because, okay, so I can change the fishing effort, but only by 2% per year or something like that, right? So this is something which we have to observe. Take into account. So my set K looks a little bit ugly, right? Maybe not so ugly. So this is the collection of X and E. So this is the collection of. We didn't have the strength of muscles in this example, but it also plays a role for us to be able to determine this boundary, right? So I have to allow it in the constraint. And all of that so that I've got positive profit, or everything, profit. So, so this is after calibration, because again, the title of this slide is calibration, right? So calibration and Vicasa. So what is Vicasa? So I think if I have the problem calibrated, it would be good if I was able to compute this boundary, right? Because I want all ingredients, so to previous slide say so. Ingredients to compute the viability can contain the set of constraints K and the systems dynamics F. So here is the systems dynamics. So see the system dynamics and the system the constraint K. And I put some numbers. So just the fish biomass should be between 60 and 600, if whatever it is. We use kilograms of toneladas, tons of that. And what I am saying here is that what I have at my disposal, that vessels, and I know that I can't send less than 10% of my stock of vessels until one, and this is the economic concept. And this problem is now fed into Vicasa. So Vicasa is a piece of software I developed with my students. Viability kernel application, analysis and stimulation application. Is there any person of the Indian, but Hindu Indian, whatever background? No, because somehow, without that much intention, Vicasa is a Sanskrit word for progress. So we were really happy to have this association. So this piece of software is available on the internet. So Vicasa is a tool that creates approximate viability kernels, actually domains. Okay, and here is the address of Vicasa. Okay. Okay, so here's the front end of Vicasa, and I'm not sure if you can see, but now I see it. Right? So here you put the calibrated system dynamics. Okay. So name, variable, bounds, here, right? So and then an addition variable is the positive profit, and then this is a very important constraint. Not visible, but all these calibrated stuff you can fit it into Picasa, press a button, wait a little bit, and you will have a viability curve, right? Something like that. And that's what we did. And so I pressed one of these buttons. There are various algorithms okay. So this is the viability kernel for that one species example. How come? What does it mean? So here's the fish biomass, and here's the percentage of the vessels I use. And you will see it in a moment, but I will stay a little bit in detail. There is a boundary of profitable fishery somewhere here. And what does this mean? It means that with that 1% change of the fishing intensity, because that was what I have assumed, 1%. So this is a very slow process, very labor friendly, because with 1% they can adjust, they can retire or something. Okay, so if I start from here, I can do whatever I want to do. But if I am at the boundary, I have to use this kind of last rest of the constraint. And to see it more how this thing has come. So here is the economic boundary, right? So if I have a little fish biomass 100, and I send 50% of my fleet, I'm not gaining much, right? I can try to keep fish more, but there will be other problems with that. Because, for instance, if I had 100 kilos of tons biomass and fish 0.9, then it's still economical, but with other problems. So what are these here? So why this at this point and any point on this line is not fire? Look, we said that we can change the arrow direction only by 1% from period to period. So I'm here. So what does it mean? I'm sending almost 90% of my vessels, and I have a lot of fish. Okay, so I'm certainly within this area, which is economical. But if I continue, I say, oh, maybe I'm fishing too much. I will change it a little bit. This is a little bit very slow change, but too slow for the stock not to cross this economic boundary, because here I have changed the biomass from 600 to 150 or 130, and I'm fishing 0.8 with 100. I am not gaining much. So if I start here, I'm violating this boundary. If I am inside, if I didn't change my fleet size, I would go on the straight line here and will be still economical, okay. Here, non-economical, right? And but if I change the fishing intensity much faster, I will go probably like that. What is this? The steady state line. So the steady state means that that's ideally here where I should stop. But because of hurricanes and things like that, I will probably in the next year a little bit off this line, and as long as that wind has pushed my biomass not here, I will be able to recover. Okay, so this is the one species. Oh, what did I do? Okay. What did I do? Okay, so this is back. So I just wanted to show you some things regarding the bycatch. It's interesting, more interesting than this simple example of one species. So again, okay. So bycatch, it is modeled in a very simplistic fashion. So we are saying that the Y species, the other species, the bycatch species, will be caught a fraction of what I am fishing on the target fish, right? So I don't know if I have a large stock of eggs, I will also catch, numerically speaking, a lot of wine, something like that. And for numerical reasons, we have put it as from 50 to 20%. So we have now two equations for species X and Y. Well, this Y, this HY will be just explicitly written as alpha XH. And again, I'm very socially careful. I'm just assuming that I have a constraint on social sustainability. So within the, I want to remain within the K set, and here's the equation, here's the system of equations which describe how the fishery works. And for simplicity, I'm not putting penalty on the fishing that bycatch, and I'm not allowing to sell it either. So that's the fishermen just have to observe a constraint like that. So this is the new constraint set. X has to be greater than 60, and Y has to be greater than 30. Right? And profit has to be positive, and I still am very cautious socially, just 1% change. So I'm fitting now this problem into the CASA, and here are the 3D pictures. So here's the target biome. But I can turn this so that we can see better what this picture says. So I've got target biomass, and I've got bycatch balance. What is it? This is the viability number. What does it say? Well, it says more or less, or it says similar things. The one species example told us. Look, if I have little biomass, if I have small biomass of the target, right? And so I can't, I am outside the viability kernel because I'm not fishing enough to satisfy my economic constraint. Here's another thing. So if I have a constraint on the bycatch 30, so I with 50, you can see that there is something missing in that, or very a bit irregular, but there is missing this part. What does this mean? This means that if I'm fishing a lot of target biomass, but the bycatch is smaller, then because I said that 20% of what I catch as the target fish, it will be the bycatch, I will ruin the bycatch species, right? So that's like that. So I can, you can see this. This is precise. That's the same boulder, right? But this is the same figure. Here explicitly you can see that with the bycatch being small and the target being large, this is not the entire figure. I can't be outside this yellow thing because I will be in troubles with the with the species, with the bycatch species, right? And okay, so and so now, okay, so now I can analyze it a little bit in detail. So I can analyze what would happen if I have a lot of bycatch biomass. If I bycatch biomass is so I would cut this three-dimensional thing in here. If it's small, I will be cut it here. Okay. So I can see. So this is and this surprise, it looks exactly as the one species picture, right? Because I have a lot of bycatch, so I 10-20% it will reduce, and that's like and but if I have a this is the point which is outside the viability, and then I will show it. Much nothing, right? Okay, so but anyway, this is the point outside the viability kernel, because this is missing, because the I cut the three-dimensional figure where there was little bycatch fish, right? So, and I know that if, especially if I have a lot of target biomass, I will be catching 20% of this number as bycatch, and I will ruin the bycatch species. So you can interpret this practically. And here's one example, numerical example. You can compute with Vicasa what happens if you start inside the variability kernel, and what happens if you start outside the variability kernel, depending on the. Yeah, so unfortunately, I have no time now to explain it, but well, you can look at the other slides if it's recorded, or we'll see what happens, right? Okay, so I have chosen 2 points which are only different by the fishing effort, but that's intuitively obvious. I'm fishing too much. So if I am fishing too much, I will diminish the target biomass and will leave this box. What is this box? This is the set K of where I want to live, where I want to live forever, right? And okay, so that's a different picture. I can tell this viability can work with the software and like that. And then you can also examine the time profiles. What happens if you change the fishing effort regarding these guys, and they saturate eventually. But if you are starting from a wrong point outside the variability kernel, that's here, and immediately, well, with this large target biomass, you diminish the population to be below the constraint, and the system is unstable, and even if I try to diminish the effort, I can't do it quick enough to keep this above this boundary. Okay, so I think I can sum up. The viability can provide us with an overview of the space in which the fishery can evolve. The analysis will help the government to select a sustainable fishing policy because, as I said, once I'm inside the viability kernel and not very close to the boundary, I'm not afraid of any hurricane. Right? So that's regarding the example presented. The notion of viability theory should be now more clear to you. And because this is a numerical area of mathematics, so we should think of computational algorithms that would lead to kernel determination, sort of not vulnerable to the curse of dimensionality. Because I have to admit that for 2 dimensions, 3 dimensions, 4 dimensions is okay, but for 21 dimensions, forget it. That would be that would saturate the computer for years. I think to get maybe with some better algorithms would be okay. So I think this is muchas gracias. So I think I'm thanking you for your attention. And I'm thanking you for your question, because it's always good to have a question which tells us that there's some echo of what I was presenting to you. So, gracias. Por favor, pregunten.
Muchísimas gracias, doctor, por su presentación. La verdad que es un poco complejo en su conceptualización matemática. Sin embargo, bueno, creo que brinda algunas bondades, ¿no? Normalmente estamos acostumbrados a pensar en enfoques en donde se generan estrategias de manejo óptimas. Y bueno, la idea es como pensar en un escenario en donde tengamos posiblemente diferentes valores que puedan ser viables, ¿no? En función de las estrategias de manejo que pueden variar a lo largo del tiempo, en función del esfuerzo, etcétera. Y bueno, creo que es un enfoque que valdría la pena por lo menos analizar y es interesante en ese sentido. Pasaremos a la sección de preguntas y comentarios. La idea sería primero pasar por las personas que se encuentran aquí en el salón y si posteriormente haya alguien que quiera comentar de lo que se encuentran, nos siguen en Facebook, lo podemos hacer. Vamos a preguntas. Las preguntas pueden ser en español, inglés, sin ningún problema.
¿Qué quiere decir con la parte social, la sostenibilidad social? ¿Son empleos? ¿En este caso? ¿Son empleos?
Sí, esos porcientos que pusimos en qué tan rápido cambia y es esfuerzo de pescar. Y si pusimos con este constraint la restricción de 1%, eso quiere decir que la mano de obra cambia, es admisible para que cambie de manera muy lenta. Y esto hace que el viability, que el núcleo de viabilidad es relativamente chico, porque si yo pudiera cambiar de un día para el otro, 80% de reducir, podría pescar más hasta cierto momento, y en este momento sería socialmente admisible echar la mitad de mano de obra Y el fishery, va a recuperar. Porque sí, con ese, con ese, con ese cambio lento, yo no, yo no, no se deja de ese, no se deja en la extinción por el cambio lento. Pero si yo pudiera cambiar la manera de manera rápida,
Sí, sí, entendí. La otra pregunta.
¿no? Podemos. De bajar más rápido, porque eso es el esfuerzo y con este esfuerzo de menos 1%. Con este biomasa y que sería que yo no sé, tendría el esfuerzo 5%, podría muy rápido regresar a este conjunto admisible. Pero esto significaría que este límite llegaría hasta acá, porque sería previsible de cambiar la mano de obra de manera rápida. Más o menos.
Y la otra pregunta, gracias.
Ajá.
Sobre las soluciones, ¿pueden considerarse soluciones de diferencia?
Bueno,
No son probabilísticas.
no, bueno, que la probabilidad se puede allow for. Son ecuaciones de diferencias o diferenciales. Y, pero con el signo de inclusión, entonces que la inclusión dice qué puede pasar. Si en ese sería otra restricción, que no hubo presentación, sería otra restricción de no meterse demasiado. el núcleo de variabilidad sería más chico, porque no quisiera, imaginándome que cada tormenta hace muerto a 1% de biomasa, yo debería evitar las áreas muy cercanas al límite que yo había calculado. El caso estocástico se puede manejar. Si sabemos qué es el límite del daño que puede ser dado por la tormenta.
Doctor.
Okay, sí, es algo de una anécdota. Yo hablo algunos idiomas. Me dijeron que tú todavía estás joven, porque no me lo dijeron de una hace muchos. Pero ten cuidado, porque conocíamos a un señor que hablaba 11 idiomas. Entendía perfectamente cualquier presentación, cualquier pregunta, todo eso perfectamente. Pero él contestaba también en 11 idiomas. Entonces yo creo que yo logré a él a su edad. Por favor, no se extrañen que estoy mezclando y porque es difícil de switch.
Muy interesante el plática, doctor. Y tengo dos preguntas. Las voy a hacer para que una vez las. La primera tiene que ver justo con cómo se construye una gráfica como esta. Y me imagino que de todas formas necesitamos hacer la estimación de los parámetros de gráfica profesional.
Definitivamente.
Para poder tener esos límites con cierta certeza, con cierta aplicabilidad, debemos de todas formas optar por esa parte metodológica de conocer la dinámica de la
Bueno, pero no hay títulos de las diapositivas. Algunas eran calibración. Entonces, tenemos la idea de cómo es la población y estamos analizando los datos históricos y encontramos parámetros para calibrar el modelo. Claro que esos son resultados de una calibración, porque para otra calibración sería eficaz.
Y la otra pregunta es de enfoque. No sé si usted está familiarizado con un trabajo de Cali sobre puntos, es un trabajo sobre puntos de referencia para el manejo pesquero. Y en este trabajo se habla sobre justamente el problema de tener puntos de referencia, o más bien la propuesta de trabajar sobre puntos de referencia óptimos y puntos de referencia o límites y objetivos, porque habla un poco del problema.
Sí.
El MSY, el rendimiento máximo sostenible, es en realidad un punto de referencia que debería de ser considerado un límite porque pone en riesgo a las poblaciones. O sea, te pasas un poquito y ya estás del otro lado. Entonces, este enfoque es muy parecido a ese problema.
Yo diría que la biomasa de aquí, que se supone 600, puede ser sí, debe ser Aquí pusimos como cambio capacidad. Capacidad de corrección. Pero sí, y punto de referencia podría ser, digamos, algo en esta línea que es la línea de estado estable. Para aquí en medio, porque para un estado seguro. Entonces se podría calcular, ¿no? Y nada más, ¿qué tal si quisiéramos pensar en un modelo estocástico? Ya estamos aquí relativamente cerca de la frontera. Y si hay un viento o algo que disminuye la población, la masa, podemos estar aquí. Entonces, con esos con el movimiento lento de la mano de obra, esto tendría ser propuso con cuidado, ¿sí? Porque estamos relativamente cerca aquí. Si proponemos un punto aquí, no es un punto estable, entonces el sistema va a evolucionar. Pero con controles podemos mantenerlo. Gracias.
Hola, buenas tardes. Muchas gracias por su plática, está muy interesante y sobre todo último la aplicación del análisis. Entonces, me surge la duda si este análisis puede ser aplicado, creo que sí, no sé, lo que es el grado de incertidumbre, ¿no? Sobre modelos de referencia del stock.
Sí, porque eso es lo que hablamos yo lo llamé el modelo estocástico.
Pues puede ser entonces en sustitución, por ejemplo, lo que tradicionalmente se aplica, que es estadística bayesiana o la simulación Monte Carlo, promostreo.
Bueno, si hicimos simulación Monte Carlo, podemos tener de la variancia del ruido. Entonces, con esa información de varianza del ruido, de lo que puede pasar con el viento, podemos aconsejar que se mantengamos no en el límite, pero un poco más adentro. Y ese margen que tan fuera adentro del núcleo estable sería un resultado de la información que es la teoría y una cambia del contexto.
Sí, está bien.
Sí. Entonces, en estos ejemplos no tuvimos está todo y pusimos números después de una calibración imaginaria, ¿no? Pero con incertidumbre sí podemos limitar la incertidumbre de la historia que los huracanes no hacen más daño de un cierto porcentaje. Podemos
Con respecto a los beneficios, ¿cómo sería la diferencia entre incluso los vainas entre los dos biomasas, hay más.
Sí, sí, so, bycatch.
El bycatch.
No, I think, no, en este modelo, el supervisor de esta región pescado impone la restricción a los pescadores que la especie bycatch no pases un límite por abajo. Pero se podría, y no paga ni multa, ni puede vender. No, sí. Entonces, pero sí tenemos, se puede incluir una multa o se puede incluir un precio al cual está bycatch biomasa se podría vender.
Acá tienen una pregunta.
Hay una pregunta del público que nos está viendo en Facebook. Pregunta Wendy Espinosa. ¿Cuántos años de información se necesitan para calibrar el modelo para una especie?
Bueno, con Juan Carlos trabajamos en el caso de Abulón. Y tenemos 10 años de historia, pero el modelito que proponemos no diría que sería muy confiable, porque entonces datos actuales de 10 años, estos son nada más 10 puntos. Entonces, tanto puntos más, tanto mejor el modelo. Pero se puede empezar con lo que tenemos, porque el paso adelante es de presentar lo que estamos haciendo con Juan Carlos a ustedes y esperar comentarios que sí, la calibración parece justa o no, de ningún modo, por ejemplo. Porque tuvimos esos datos de 10 años, propusimos un modelo y reproducimos la historia del modelo, que visiblemente no es tan distinta de la historia verdadera. Entonces, es más bien una estimación por ojo. Bueno, sí, podemos calcular la variancia, promedio, cosas así, pero entonces yo diría que 10 puntos es lo mínimo. Bueno, eso depende del tamaño del modelo, porque si tuviéramos un modelo con no sé, 6 variables, 10 años sería menos, el modelo basado en 10 años sería menos confiable, porque en nuestro modelo, bueno, tenemos 3, digamos, parámetros que se identifiquen. Entonces, eso depende del tamaño del modelo. Bueno, yo creo que la teoría de probabilidad dice que 30 es un límite para tener un promedio que se puede confiar. Pero aquí en este caso no tuvimos.
Pues muchas gracias. Tenemos otra pregunta del público en Facebook. Pregunta Martín Salgado. ¿Es posible incorporar resiliencia humana a la teoría de viabilidad y cómo?
Injerencia humana.
Resiliencia.
Residencia.
Resilience.
Residencia. ¿Qué es?
Resilience.
Human resilience, pero ¿qué es eso?
Social resilience.
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 Resilience. ¿A qué? ¿De qué?
Into the model.
Social.
Social resilience into the model.
Pero resiliencia ¿a qué?
No dice nada más.
No, porque
Ahorita parametrizar.
porque, porque yo lo que digo pensar es una estrategia que sea resiliente a huracanes, por ejemplo. Entonces, es de lo que dije que los límites serían más
Estrechos.
estrechos, sí. No sé.
No. Déjame enciendo. Ahí está.
Bueno, buenos días. Gracias por la presentación. Yo tengo una duda cuanto a la utilidad de esta herramienta, si está enfocado o permite estimar como punto de referencia el máximo rendimiento económico para, digamos, optimizar el aprovechamiento de un empresario. Y si es así, ¿qué casos puede comentar que esté trabajando?
Pues, el núcleo de viabilidad dice dónde podemos permanecer sin mucha preocupación de choques medianos o chicos. Y can you rephrase your question?
Sí, para efectos de manejo se puede estimar el punto de empresa y el máximo rendimiento económico y qué ejemplos pudieran mencionar.
Bien, bueno, como decimos, puntos de referencia pueden ser que nos limitan el máximo de la población y el máximo de la. Y también un punto ideal, digamos, desde el punto de vista del manejador, porque el manejador puede, por varias razones, el conocimiento de los vientos, pero también conocimiento que viene de ciencia, de preferir un punto aquí. En un otro fishery semejante, con tal vez números muy parecidos, se preferiría de estar aquí. Entonces, esto es esta libertad que proponemos al manejador, que, mira, nos dijiste todo a propósito de los vientos, de la población, qué tan vulnerable sería el mano de obra a empleo, desempleo, cosas de éxito. Y aquí está el momento en el cual puedes permanecer.
Sí, me acordé que en la presentación de su perfil, discípulos que vienen de la Universidad de Australia. Y yo recuerdo que hace tiempo uno de las colegas trabajaba en una pesquera, una colonia, y la otra comentaba que en esta área de Sydney es tanta la pesca ilegal que la incorporaban como una variable más dentro de su modelo de evaluación. Esa sería la idea cuando usted puede marcar en el museo.
Sí, porque estamos direccionando nuestros esfuerzos en especie X, pero ¿qué tal cuál?
Estamos también y si pescamos demasiado Y, nos penalizamos. Es un modelito bastante simple y pues, si quieren hacer la referencia de la primera referencia del modelo así es del muchacho francés Benet en Ecological Economics.
¿Existe algún otro comentario, pregunta para el doctor? Bueno, actualmente estamos trabajando con el doctor, estamos trabajando con el enfoque de viabilidad, estamos incorporando con el experto Paulón, son los datos que tenemos disponibles y la idea es posteriormente pues, hacer una plática sobre los resultados de simulación que están saliendo. Ya es calibrar el modelo, ya se encuentra calibrando y bueno, estamos explorando las salidas que ofrecen, ¿no? Para que sea algo más digerible, contexto más local y la factibilidad de poder concertar diferentes escenarios que pudieran ser viables y concertarlos con ustedes, que pueden tener un contexto más local, ¿no? de la pesquería y eso lo haremos más adelante. Si alguien se quiere poner en contacto directamente con los doctores, vamos a enviarles su correo electrónico para que puedan hacer contacto. Les enviaremos también la presentación del doctor y algún par de artículos relacionados con el tema para que podamos tener un mayor contexto. Si no hay más preguntas o comentarios, pues agradecemos mucho la presencia.